Hello everyone, this is homework 2. We have basically two questions here, and one of the questions will be a PDF file, so you will create a report for question 1, and the other one will be a MATLAB file, rlocus_info.m file for question 2. Now, first of all, we have a second order transfer function given here. We have the natural frequency, which is a positive value, and we have zeta, which varies between 0 and 1, but 0 and 1 are not included, which is called the damping ratio. The settling time needs to be modeled, and it is known that the formula has the following form. So we know that the settling time has a special form like this. And the first task is to use the mesh grid function of MATLAB and the integral squared error, the ISA, of the difference between the actual settling time and the settling time calculated using the formula of this here, to basically minimize this ISA here and to come up with the coefficient that needs to be placed in here. So this is basically a manual version of the second task, which is to use the MATLAB fit function. So the question is basically the following: code it for MATLAB fit function using MATLAB fit function, use the MATLAB fit function to come up with the model here, but also only for the settling time here, do it using the for loop and mesh grid function in MATLAB, just barely coding here. And the strategy is the following: you will use the mesh grid for your domain, and the domain is given omega n and zeta. So zeta is basically between 0 and 1. We know that. Pick an interval for omega n, large enough to have the right model, but small enough to be able to compute it on your computer. So pick that omega n vector, pick a zeta vector, use the mesh grid to generate basically matrices of these, and then you will also have an additional vector for your coefficient, which can be between, let's say, 0 and 10. And then you will just pick each value of this vector for the coefficient, evaluate the integral squared error over the mesh grid domain, and you will basically have a single vector corresponding to each coefficient has this ISA value, this integral squared error, and where it is minimum, this is basically the coefficient that should be there. I hope that this is understood. This is basically brute force methods to try to come up with the actual coefficient that fits. You use the MATLAB fit function. Again, the same goes for rise time here. You need only the MATLAB fit function for these two. There are two different rise time formulas. Just go ahead and use MATLAB fit function for both of them and provide the results. So you can just give graphics and stuff and documentation, because you will generate a small but comprehensive PDF report for question 1. So the theme is basically I've picked this omega n vector, I've picked the zeta vector, and then if it would be nice if you can just show, for example, the domain that you have picked on the S domain, for example, and then also show maybe the coefficient versus ISA plot, and then that the corresponding coefficient is the minimum. Give some numerical data. The minimum ISA occurs at this coefficient with this, and that should be sufficient. So just a small guide through this first part here will be necessary. It will be sufficient. And then you can just give the fit function here on how you have used it. Rather than overcomplicating this stuff with code, I just want to see some results. We have a certain table, and then there are the results. This is how good it fits, etc., etc. So I want to have more of a explanation than MATLAB code. So Q1 is just a PDF report. As you can see, I didn't ask for your code, so don't give me code for Q1. Just give me explanations and a small maybe plots and stuff so I can see what you have done, basically. Q2, however, is directly a coding question here. We have a rlocus info.js. It will return an info structure, and I guess there's a little problem here. Sorry. We have 10 points, 10 points, 20, 40, and then 30, 30. It should be 60, not 30. Okay. Now, calculate the breaking points on the real axis on the root locus of the provided transfer function. So, first, we are going to calculate the breaking points of GS on the real axis in this function. We are also going to calculate the j omega crossings of the root locus, again in the function, and put it in a special structure and return it. That's basically it. And therefore I have this file prepared for you. Again, the same structure goes on like this. We can just give it a transfer function, call this info here, and the output should look like, did I include any output here? No. But the output structure here is given, so let me show you that. You convert this into a symbolic expression, calculate the real axis breaking points, and store it in B points, calculate j omega crossings. We will calculate the gains and the crossing frequencies in k and omega respectively, and then you put them into a struct, B points, k, k, omega, omega. Don't change this, don't change the variable names, don't change anything, just fill in the gaps here, just implement the necessary stuff here. When I call it, I will be looking at B points, k, and omega values, if it's correct for certain transfer functions that I'm going to try out here, for example. Then it will be graded. And this rlocus here is basically 60 points worth. So this function is 60 points worth and a 40 point worth PDF file. So that's basically the composition of our homework. So let me recap. We have a second order transfer function. We have zeta omega n. You will define a domain. Over this domain, you will calculate each difference between the actual settling time that you can use from step info, because you have all the necessary data here, and you will basically have first of all a domain in the S domain in terms of zeta and omega n, and you will have a coefficient versus ISE graphic, for probably. It would be nice to plot something like that and show that the minimum occurs at a certain coefficient. You will write a report for Q1, a small one, but hopefully that explains stuff well. And then repeat this with the MATLAB fit function, and also just use MATLAB fit function for rise time, for the first order and second order rise time formulas, and provide the results basically. Small report for Q1. And Q2, you will have access to main.m and rlocus info. There are the breaking points on the real axis that will be calculated here, and we have some crossings on j omega. The gains, the frequencies, the breaking points, they should all be calculated and stored in the corresponding variables, so that when we use root locus info like step info, we will get .settling time, .overshoot, or in this case .b points, .k, .omega, so we get this data from this function here. So hope that everything is clear. Again, please don't submit main.m file, you just need to submit the this file only, rlocus info. I'm going to give it to you, and good luck.